the meeting. So I have that just before a minute. I think in my quarter or in this area, in this campus, some area where the power has been shut down. So that was the reason for the delay. Yeah. Okay, so let me share the screen. Okay. So is the screen visible?
Yes, sir.
Yeah, right. Okay. So so in the last class, that's last Friday, so we started the discussion on the memory, basically the hierarchy of memories, how it will affect the performance of system, overall system. So in that context, we are discussing about in that hierarchy. First, we are focusing on the two in the hierarchy, the two memories that were the two memory the like the mapping between the two memories, that the main memory and the cache memory. So that we are discussing where the cache memory will be accessed by the CPU first, and if the instructions or the data, if they are present in the cache memory, then it will be accessed from that. Otherwise, then a miss will generate, and then the desired data from its lower hierarchy will be brought into the cache, and then later it will be used. So, so in that, we discussed about one of the techniques for mapping the main memory to cache memory. We know that the main memory size is much larger compared to the cache memory, right? But the cache memory access time is much faster compared to main memory. So therefore, we'll try to see that whatever the CPU requires, the instructions or data, whichever the portions of the data or instructions that are required. So that will be try to place it in a cache so that whenever CPU requires any instruction or any data, it will first check the cache, and mostly it will be available from the cache so that there won't be any wastage of time. And within a clock cycle, the things will happen. And now, but as we have seen that the program size will be much larger than the cache size, and so therefore the most of the program that is instructions or data, so that will reside in the main memory, and then the portions of the program whichever is required at that particular point of a time, so that will be placed in the cache so that the CPU can access the cache. And for that, the mapping between the contents that are present in the main memory to the cache memory. So there are various techniques in that last class we discussed about a technique known to be one of the simpler one, known to be direct mapped cache, where we have discussed about with this example and all. So if you look at here, there are about 32 words are there. Assume that the main memory size equals to 32 words, or a program size equals to 32 words, for example, that are there in the main memory. But your cache availability will be having, it can able to accommodate only 8 words. So in that case, the way these 32 words are mapped to these 8 words available, or 8-word storage of cache. One way is that known to be direct mapped cache. So it means that the multiple words of the main memory will be pointed to a single location. So here there is a 32 words has to be placed into the 8 words. So therefore, 4 of the words have targeted or have located in one location and all. That means out of these 4 words, only one word can be placed over here, and that depending upon the CPU requirement. So that particular word will be placed. Suppose if there is some other word is required, then this word has to be replaced, and you have to place some other word. So that way, whatever the physical address of these particular words, all of them are mapped to a unique location, separate unique location into the cache and all. For example, if you look at this particular entry, like a blue colored one, And this for his the cache entry corresponds to this will be the location 5, location 101. And for this location, this particular location is mapped from the main memory locations at these positions. You can see like 111 followed by 01, 101 followed by 01, like 011 followed by 01, and 001 followed by 01. So for all these 4 blocks or 4 words, they map to a single location, and they map to a single location. Likewise, even for the other set of 4 words also, they'll try to map to a single location here. And so therefore, in principle, like for every word in the main memory, so they have a unique location in the cache entry, in the cache storage or in the cache memory. And so this is one way to like map the like the addresses of main memory to a cache memory and all, to a cache memory. And we have seen with an example, and we also discussed about what are the tag bits, what are the valid bits, what is meant by block. So all these things we have discussed in the last class, and we have shown with an example also. This was illustrated here. And so this was the architecture, like you can say that the overview of the cache. So it means that given the physical address, how do you find out, how do you first of all search the cache entry, whether the desired address or the desired word that is required, the required word, if it is present in a cache or not. The required word, if it is present in a cache or not. So that you can able to view from this diagram. And here you know that suppose, for example, if the bus size equals to 32-bit, so the CPU generates the 32-bit address, right? And assume that your cache size equals to, as per this diagram, the cache size equals to 4 kilobytes. It means that it can accommodate 4 kilobytes of data. And as per this, the addressing mechanism, whatever here mentioned over here. So here the cache, each cache entry stores one word. That is the block size contains the one word. And here in this terminology between the cache and main memory, the data unit will be treated as a block. A block may contain a one word or multiple words. So in this context, a block contains one word. You can see because as per this, there 32 bits are divided into like 3 groups. One is the byte offset, and then the byte offset is represented by 2 bits. It means that the remaining next part is the block 1. So that therefore each block contains 4 bytes. 4 bytes. It's nothing but a word because there are 2 bits are allocated for this 1 byte offset. It means that 2 bits means like it can address the 4 bytes. So therefore here this is nothing but from this what we can infer is that a block is nothing but one word. Block is nothing but one word. And here the block is represented by the number of blocks that can be accommodated by cache is indicated by here the bits, number of bits 10. Because you can see there are about 1024 entries in the cache. So to uniquely represent this 1024 entries, we require 10 bits are required. 10 bits are required. So this is the cache index, where each the cache index refers to like each entry in the cache and all. And here the cache usually cache contains or cache stores the data in the form of blocks and all. So here it so happened that the block contains one word. Block consists of one word. So therefore this 10 bits refers to the index, cache index, right? And or is also known to be like from these 10 bits we'll come to know that given the address we'll take these 10 bits, and from these 10 bits we'll go to the corresponding entry into the cache. And so that way we just based on these 10 bits we directly go to a cache location based on index, and then we'll check whether that index, whether that particular location contains the desired word or not. So for knowing that, actually here these 10 bits indicate the block, the specific block and all. Whether this specific block is the desired one or not, that is decided by these 20 bits, the remaining 20 bits. The remaining 20 bits, they are not to be tag bits and all. So along the cache entry, because the total address size equals to 32 bits, right? But the cache can contains only 4 kilobytes. So therefore, if you try to see that the size the storage that is offered by cache to the total address space will be like the total address space is about 2 power 20 times that of the cache size. So therefore, here these 2 power 20 words, out of these 2 power 20 words, whether the desired word is present over here or not, that we have to check it out, right? So for that purpose, here these 20 bits are used to find out whether the word that is present in this cache location is the desired word or not. So for that purpose, actually here, this higher order 20 bits or known to be tag, that also has to be maintained by the cache and all, because here this gives you the block number, but such blocks will be there in the address space. There are huge number of such blocks will be there, but in that the desired block, whether is it the desired block or not, for that along with this the block number, it should also contains the higher order bits, the 20 bits, the specific block. So these 20 bits indicate the tag and all. So that also has to be maintained by the cache and all. So once by using this index, we'll directly go to a specific location to a cache, and at that location we'll just check this because it contains a block, and that block has some tag number and all, whether this tag number is the one, the desired one or not. So therefore, this particular tag number that is stored in a cache is checked with compared with the higher order 20 bits of the address generated by the CPU. So that will be compared, and if both are matches, it means that the word that is required is present in the cache. So it generates one, and also here, as I already mentioned, that the significance are the valid bit, the use of valid bit and all, right? So if both are satisfied, then the AND gate will generate one. It's nothing but hit. It means that the CPU generated address, the block specified by the CPU generated address, or the word specified by the CPU generated address is present in the cache, and then it will be fetched, and then the CPU will it will be passed on to the CPU so that the CPU performs any arithmetic or logical operation, whatever is required. So this is the way the cache will be accessed by the CPU, and check that where is the data, and in that location, is that the desired data is present or not. That will be checked by using tag and valid bits and all. And here in this example, we considered the size of the cache equals to 4 kilobytes. And here, when I mentioned the size, means the size refers to here the data. It's not the total size of the cache, because the total size of the cache includes the tag bits and valid bits. When I say in general, when I say the size of the cache, means we mentioned that what is the cache offered to the data, size of the cache offered to the data, and these are the like the control information that is required to verification, to check whether the entry is present or not, or whether the word is the desired word or not. For checking that one, we use this control information. The actual data is this part, right? So this is the 4 kilobytes of data, and here the block consists of only one word, and that is the scenario for this particular cache organization. Okay. So this is the simple example, the same example, just with the diagrammatic illustration. The same here also we have total 32 words are there, and the block size equals to 4 bytes. So that's why here the last 2 bits are indicated, just because here we're considering the blocks as the words. So therefore we are not bothered about the lower order 2 bits, because this is the byte offset, right? And the next 2 bits indicates the word number and all, and then the later 2 bits indicate the tag. Later 2 bits indicate the tag portion and all, because here you can see these are there are 32 such entries were there here, and and here not 32, sorry, there are 16 words are here in this case, right? There are 16 words, and our cache size equals to 4 words. It can able to accommodate only 4 words, and 16 words, and here it can able to accommodate 4 words. So accordingly, here these are the actual 16 words, means the at the byte level, when you try to address the memory with respect to byte addressing, you require six bits, because 16 words, each word requires 2 bits. So 16 words means it requires again 4 bits. So 4 plus 2 total 6 bits. That was the format over here. And we are not interested about a byte, so therefore it was mentioned as it's not really bother whether it's a first byte of the word, second byte of the word, whatever it is, right? And right, so the words matter. So therefore, the words are highlighted here, are mentioned by the corresponding 2 digits, right? And then the dull colored 2 bits are indicating the actual tag bits, the tag bits and all, right? So here, this is the cache here contains the 4 words, right? Can manage to store the 4 words, and here there are 16 words are there, and then how to do the mapping and all. So yeah, as I mentioned, the lower order 2 bits indicate the bytes, and the middle indicate the word number, and the higher order 2 bits indicate the tag and all. And yeah, here, yeah, how do you find out? We already mentioned the next two. Yeah, use the next 2 lower order bits. That means here these 2 lower order bits. So those are the indication of the word index that is to be present over the cache here and all. And the higher order 2 bits indicate the tag and all. So with that, you can able to discriminate, because you see there are only 4 storage locations in the cache, but there are 16 words are there. So it means that here, each cache location is targeted for 4 of the words in this main memory and all. 4 of the words in this main memory. So that tag, it resolves that. So out of these 4 words, which word is present over here in the cache? So that will be resolved by using the higher order 2 bits of the address and all, right? The middle 2 bits of the address that are indicating the word, and then lower 2 bits indicate the byte offset and all. Yeah, you can see here and all, you can see the shaded or the pattern here that indicates here. You can see the bottom one with the green colored dots and also where this particular cache entry or cache location that is mapped, this particular location is corresponds to these 4 locations in the main memory and all. So likewise, you can see the other patterns also corresponds to the specific locations and all. This is just one, whatever we have discussed. And yeah, now you can see here just the tag bit, just here shown with a rectangular box, brown color box and all. Rectangular gray colored box. So these are the tag bits. So those are just for illustration purpose. You can see that. So these are the various tag bits and all. These are the various tag bits, because you can see here the index is 10, right? So it means that if you look at here, this particular index, the index of the word, that is because all these words indicated by 10, 10, 10 and all, but that means that all these 4 words are mapped to the same location. But it will be resolved based on the tag bits here, which of the 2 bits are there. So based on that, it tries to resolve. If it is 00, it means that the word present over here is this one. If it is a 01, this one. If it is 10, this one. If it is a 11, this one. So it means that all these 4 words are like mapped to the single cache entry or the single cache storage and all. And that will be resolved by here the tag bits. So that's why the cache also contains the data word, that means the actual word, and along with that it also carries the tag bits and all. So with these tag bits you can able to resolve like which of the word it is present and all, among these 4 possible words, which word it contains and all. So that way the tag bits are used to resolve whether the word that is required by the CPU, whether it is present over here or not. And these 2 bits that are used to index that, directly the moment once you know the 10, it directly goes to all the words starts with 10. So they will be here. They will be targeted to only this location only. But there are 4 such possible words are there. So those 4 possibilities can be resolved by using the tag bits, whether it is like the most significant 2 bits, where it's a 00, 01, 10, 11. So with that you can able to resolve it, like which of the 4 words is present over here and all, right? So here in this case, the block size equals to only one word, right? And yeah, the same thing, whatever. So if the same diagram, continuation of that, if you take this particular example, suppose these are the sequence of references, addresses generated by CPU, for example. And if you try to look at that, the first one, because since it is empty cache, so based on the valid bit itself, we'll come to know that this particular entry is not there in the cache. So therefore, we had to brought it into that. So therefore, miss was there. So likewise, for each of these references, if you look at here, I'm just, if you look at here, just one by one, you can able to see that. Yeah, right. Right. So you can see here when a zero is called, when a zero is referred by CPU, at that time the entire cache is empty. So therefore the miss is generated. Then when you call one, again a miss was generated. When you call two, miss was generated. Three, miss is generated, because these are the initial references where the cache has started with empty. So therefore all of them, all of these, the first initial 4, 5 and all, they resulted the misses, because there is no other way, because the cache is initially empty and you are calling your fresh reference and all new references, so they are not there at all, so you have to brought into the cache. So therefore all these initial references in any program and all, it results to be misses. So these misses are known to be compulsory misses and all. We'll see that later on actually, because these misses are generated because we are just starting the program. We don't have a knowledge that actually where the which of the because the program having a very larger size, lots of modules will be there, from where the actual which of the instructions will start execution. So that is not aware of that. So therefore we don't bring anything. So therefore initially we'll have misses will be generated, and then later on you can the program will reuse those instructions later on based on its temporal and spatial locality and all. So that way here for these eight references, 8 or 9 references, if you look at here, you can see that out of these 8 references, we got about 6 misses there, and there are 2 hits are there. There are 2 hits are there. That means you can see these 3 and 4 are already it's earlier they have been called. So therefore we can make use of them for reusing that, right? And sometimes suppose you can see here 15 we have called here, but that 15th location is supposed to be here, but that was there is some other data, some other the cache is occupied with certain some other thing. So therefore we are replacing that. That means we have to take out this, and the word corresponds to present in the 15th location, that has to be brought into the cache, and it has to be replaced with the existing one. So yeah, here since here the block size equals to one word, so you can able to see that for this particular sequence of references, 8 requests, we got 6 misses and all. We got 6 misses, and now we'll see that yeah, the same thing we discussed. Yeah, right. Now we see that suppose for example if the block we consist of block assume that if the block consists of 2 words, for example. Earlier one example is that a block consists of single word. So therefore, for these particular 8 references by the CPU, it generates about 6 misses and 2 hits. Right? Whereas if the block, suppose if the block size is increased to 2 words, for example, if the block size increased to 2 words, then if the block size increased to 2 words, then then the cache will be, because as per the earlier example, the cache can able to accommodate only 4 words, right? So if you maintain the block equals to 2 words, then the cache number of cache entries will be only 2, right? Number of cache entries will be only 2, and where each entry supports 1 block, where here the block size equals to 2 words, right? So if you use this one, if you use the block size equals to 2 words, then for these set of references, the cache will be occupied like this. You can see that when a 0, when you first initially called for 0, at that time here the block size consists of 2 words, so 0 and 1 will be in 1 block, so the both will be brought into that. Then for the second reference is 1, already it is present over here because of the spatial locality, or the spatial based on the principle of spatial local, because this is just next to that one, and we brought the block. So therefore in the block the following instruction is also available. Like next, when you ask for 2, it's not there. Then when you just bring the 2 along with the 2, we also got, like with respect to 2, 2 and 3 also we got. The next is 3. So we got 3 also. Like 3 is also already present, so the 3 becomes hit. So likewise, when you fill it, when you for this particular sequence of references, and when you try to fill up the cache will be like this. You can see. Yeah, right. So here for these 8 requests, and if you manage the cache with a block size of 2 words, it results to about, for these 8 requests, we have only 4 misses will be there. So what it indicates is that if you have a cache, in that cache, if you consider the blocks with multiple words, then the miss rate will be decreased. The miss rate will be decreased. Earlier we have seen that for 8 requests we have 6 misses were there. Whereas here in this case, where the change here is that we use the same cache size, but here the entry of a cache is managed by the block size of 2 words, whereas earlier it is a block size of 1 word. So because of that, earlier we have 6 misses, but whereas here we have only 4 misses. So therefore, for handling these misses and all, there's some penalties required. So compared to earlier, this is better, right? So this way you can see that as the block size increases, obviously because of the spatial locality, you can you can improve the performance and all. After just these 2 examples, just to illustrate that actually if you have a cache with a block size of only 1 word size, that is the lowermost one, or the one extreme of that. And in that case, how the miss rate used to be there. Then if you increase the block rate just with the next level, instead of 1 word, if you consider the block as 2 words, and with that we have seen that there is an improvement in the performance and all. That means that number of the miss rate has been come down a little. Okay, so now after having that, now just let us see that, as I mentioned earlier, a cache contains the data, and as well as the data, it also contains some control information also. So with that, actually, if you try to see that actually, what will be the how much control information the cache contains, or how do you find out that what is the total cache size, including the control information. So if we take a previous example, for example, we know that the CPU generates address of 32-bit address, 32-bit byte address. CPU generates a 32-bit byte address, right? So in case of direct mapped cache, suppose if you take the mapping of cache and direct memory, if you use the direct mapped cache, for example, direct mapped cache, then assuming that a cache can support 2 power n blocks, a cache can support 2 power n blocks. It means that how many entries used to be there? There are n entries because the cache supports 2 power n blocks. So this n in the exponent part, so that provides you the number of bits. The number of bits. That means the cache supports a 2 power n blocks. So therefore, the total number of entries are 2 power n, right? 2 power n entries in the cache and all, where each entry supports 1 block. Each entry can store 1 block. So therefore, to index this cache, we need n bits. We need n bits. We need the n bits and all. So n bits for indexing the cache and all, right? To locate the block in the cache, we need this n bits and all. And again, each block contain, assuming that each block contain some the 2 power m words. Each block contains 2 power m words. It means that suppose if it is only 1 word, then this m happens to be 0. This m happens to be 0. If it is a 2 words, for example, then this m happens to be 1. If it is 4 words, m equals to 2. So like that. So the block size, based on the block size, suppose assuming that the block contains that 2 power m words, 2 power m words. So therefore, the block size in terms of bytes will be 2 power m plus 2, because 2 power m words, where the word contains 4 bytes. So therefore, the number of bytes in a block will be 2 power m plus 2. 2 power m plus 2 bytes are there, right? And then from this, you can come to know about the tag size. Can come to know about the tag size, because the tag size is nothing but higher order bits. So in the total address space, if you leave about this the the block size or block size, and then the number of blocks also, because the cache can able to occupy, cache can able to support 2 power n blocks. Cache can able to support 2 power n blocks. So these 2 power n blocks can be referred, can be indexed by using n bits and all, n bits. And again, each block can be represented by m plus 2 bits, because the address that is provided by CPU is the byte address. That means each byte is addressable. So therefore, in the total 32-bit address, if you want to see what is the how many number of bits the tag contains, or the higher order bits, where with which you can able to find out whether the cache entry contains the desired block or not. For that purpose, the total number of bits are 32. Out of these 32 bits, the lower bits, the lower m plus n plus 2 bits, so these are used to refer to the block, or these are refers to use to the details of a block, details of bytes, then the details of words, details of block, and this one, the index of the cache and all. So all these will be managed by these bits and all, n plus m plus 2. So now you can see this n is nothing but the index of the cache. That means the number of entries in the cache that indicates the n and all. And this m plus 2 is nothing but it's like number of bytes in the block. Number of bytes in the block, because there are 2 power m words are there. Each word has a 4 bytes. So therefore, this m plus 2 bits that are refers to the m plus 2 refers to number of bits that are required to represent a block. And n is nothing but like there are like 2 power n blocks are can be accommodated in the cache. So therefore, these n bits are used for indexing the cache and all, indexing the cache for a particular block. And these m plus 2 are nothing but for a particular block, these many bits are required to find out the specific byte within the block and all. So therefore, the remaining bits other than these n plus m plus 2 bits, so those are nothing but a tag size, tag and all. Those are nothing but tag. So if you look at the sometimes if you look at the previous one example, like which I can see here any of them here. For example, here in this case, if you look at here, so this is a byte offset, so words, and here in this case, if you look at here, each cache entry or each cache block contains the 4 words. Each cache block contains the 4 words. So you can see this is the first word, second word, third word, fourth word. So that is the reason that you can see these 32 bits are organized as, anyway, the last 2 bits are the least significant 2 bits are, anyway, that is the byte offset, like the bytes within a word. And then you can see there is one more partition. This indicates the word offset. That means here there are 4 bits are used to indicate the block. 4 bits are used to indicate the block. It means that the block size equals to 16 bytes, because there are 4 bits are there. So therefore 2 for 4 bytes. The block size is nothing but 2 for 4 bytes. So therefore the block size equals 16 bytes. It means that there are block kinds of 4 words are there. So those 4 words are represented by these two bits. The bits 0 and 1 indicate the byte offset within a word, and the bit 2 and 3, these 2 bits used to indicate the word offset within a block, because a block contains here the 4 words. So therefore, those 4 words are discriminated by using these particular 2 bits. And then since it's the same, this is here the cache size equals to 1 kilowords. That means 4 kilobytes, same size of the previous one. But here the block size has been changed. Earlier the block size equals to 1 word. So therefore the cache, the number of entries in the cache equals to 1024, because only 1 word is a block. The block contains only 1 word. But here the block contains 4 words. So therefore the cache, the number of entries in the cache will be like 255, 256. Because here the block contains 4 words. So therefore these 2 bits of this will go in this side. So therefore the remaining 8 bits used to index the cache. So that is the reason earlier you can see there are 10 bits over here, because the block equals to 1 word. Block equals to 1 word. So since it is a 1 word, so there is no need to index the word at all. No need to show the specific code, because only 1 word is there. But here there are 4 words are there. So to find out which word to pass on to the CPU and all, so we need to have a specific one, like these 2 bits used to indicate the specific word within a block and all. So so therefore, since it is a block now contains 4 words, so therefore the cache is now can accommodate only 2 power 8 blocks. 2 power 8 blocks. Earlier the cache accommodates 2 power 10 blocks. So the reason is that earlier the block size equals to 1 word, but now the block size equals to 4 words. So that's why now the cache accommodate 2 power 8 blocks. So therefore these 8 bits indicate the used to locate the cache index, used to locate the cache location, like indexing. So therefore 0 to 255. So those are 8 bits and all. And the remaining are like tag bits. So here now you try to see that here that n is nothing but here over 8 here, and m equals to 2 here, and anyway 2 is there, n plus m plus 2. If you subtract this one from the 32, that gives you the tag size and all. Whereas in the earlier example, this m is happens to be 0 because a block is one word only. So therefore 2 power m is nothing but where m equals to 0. So therefore there is nothing. So therefore here these 2 bits are matched with the index itself. So that is the reason that earlier you can see that the cache for representing the cache entry index, there are 10 bits used to be there because because 2 power 10 blocks will be there, each block equals to one word. Whereas here the same cache we organized in the form of 2 power 8 blocks where each block contains the 4 words, right? So to take care about the spatial locality. Spatial locality, and that means in one go we'll fetch the 4 successive words and all. So the chance is that suppose if we require this particular word, then most likely that the CPU requires the next instruction to be it's just the next word, next word, and so on. So therefore there are chances of calling the successive words also will be there. So therefore if you take a block of larger size, then it takes care about the spatial locality. So that way the miss rate will come down. Right. So this is the way you can able to compute the tag. If you know the cache specifications and the block size, right, then you can we will come to know about what will be the size of the tag and all. So basically in the here we just mentioned we discussed about that, right? So therefore the total number of bits in a cache will be total number of bits in a cache is nothing but data size plus the control bits, whatever is there. So there are 2 power n entries are there in the cache, and each entry contains a block plus a tag bits plus 1 bit for valid, 1 bit for choose either it's a valid or invalid. So therefore the total cache size equals to this one 2 power n. This is the total number of entries. That's nothing but each horizontal entry. In that you have a block, actual data bits will be there, actual block information bits along with the tag of the block, and then the validity of the block, whether it's a valid, whether the entry is a valid or not. So this way you can able to compute the total number of bits in a cache. Yeah, this numerical example illustrates the same thing with the appropriate the numbers and 32-bit address, 16 kilobyte cache and all, and block size something. So you can just go through that. Same, just illustration of this one with the form of a numerical example. And here from this, what we can understand here is that when you say 16 kilobytes of cache means it's a data size. So to manage the 16 kilobits of data, the cache requires another some additional data is required. So here you can see that. So for managing the 16 kilobytes of data, this cache requires total size of 18.4 kilobytes. It means that the 2.4 kilobytes of the bits kilobytes that is just meant for controlling purpose like a tag and validity bits and all. So that way just given the illustration that it requires 1.15 times more than the data that is required, the total size of the cache. It is 15% more than the data, whatever the data size is there. So to manage the data here in this particular case, for these specifications and all, it requires 15% overhead. So that overhead is due to the tag bits and the validity bits for each entry. Yeah, this is just again another illustration. Suppose, for example, the CPU generates the byte address, sir, and from that byte address, how do you know that actually what is the block address and what is the corresponding block number in the cache and all? So CPU generates the 32-bit address, and suppose, for example, CPU says that the block address equals to 1200, for example. A block 100 equals to, suppose a block number, you have to find out the address equals to 1200. So this 1200 is a byte address. right? And we know that, for example, if a block contains 16 bytes, so if we divide this 1200 by 16, we'll come to know about the block address. We'll come to know about the block address. So if we divide by 16, and since yeah, if it is a 1200, this is properly divides with 16. And suppose if it is a 1201, for example, or 1202, something like that. Then, so therefore, for taking care of that one, because now a block contains 4 words, so therefore you have to take a floor of that when you perform the division and all. So that way here it's a 75 you will get. So it means that this particular address, CPU generated address, this corresponds to a block, the block address of 75. Block address of 75. So, and here, yeah, in principle, how many blocks will be present? In principle, given the CPU address in this scenario, how many blocks will present? What is the size of block address? In this case, suppose here is given as one address is 1200. What is the maximum address size that is can be provided by CPU here? The suppose from the given CPU address, what is the maximum possible block number you will get? Anybody? What is the maximum possible block address? Because you see that the CPU generates a byte address, right? And we know that a block contains 16 bytes. So how do you get a block address? Simply but divide whatever the CPU address is there. If you divide by 16 to power 4, you will get the corresponding block address. The corresponding whatever whatever the address, the block address, you will get that block address. So what is the maximum possible block address you will get? What is its size? What is its like? What's the value corresponds to? 2 power 28, right? So maximum possible will be like close to 2 power 28 minus 1 or something like that, right? Is it got it? Have you got it? Is it clear why you got 2 power 28 minus 1, the maximum possible block address? Right? Anybody? Hello? Hello? Is it audible? Hello? Hello?
Yes, it is audible, sir.
Okay, fine. Yeah, can anybody, do you understand my question? I'm saying here is that there is a 32-bit address that is generated by CPU. It's a byte address. And I mentioned that a block contains 16 bytes. A block contains 16 bytes. Earlier, like forget about that. Earlier, you know that how do you convert the byte address to the word level address? How do you convert that? How do you convert the byte address to the word address? Word level address. How do you get that? Right?
Sir, 4 byte is equal to 1 word.
Yeah, correct, exactly. 4 bytes equals to 1 word. So therefore, the most significant 30 bits indicate the most significant 30 bits indicate the word address, right? In a CPU, when it generates the 32 bits, right? The most significant 30 bits indicate the word address, right? Because the last 2 bits is nothing but within a word what byte it refers to, that is indicated by the least significant 2 bits, right? The same way here also, when I say block equals to 16 bytes, right? The maximum possible block address is nothing but like, because this is of 16 bytes, so therefore the least significant 4 bits indicate the byte offset within a block, right? So the remaining bits indicate or carry the block number, simply a block number. Here it so happened that we are given 1200, so therefore this entire 30 bits refers to just indicating 75. My question is that what is the maximum possible, the block address? It's nothing but if all these 28 bits are happens to 1, so that will be the maximum possible block address you can get, right? That's what I just want to convey you, right? Just try to see that earlier we have a byte address, and then when you talk about the instructions and all the time the instructions will be 4 bytes. So therefore we used to fetch like 4 bytes each every time, right? So in that case, when you convert the byte address to the word address, what we are doing, we are just dividing the by 4. We are just dividing the by 4, or otherwise just considering the most significant 30 bits. So that indicate the word address and all. So the same way here also. Yeah, okay. So given this 1200 byte address, this is the corresponding block address, the 75, right? But here in this case, the cache can support only the 64 blocks. Cache can support 64 blocks. So therefore, what is the block number in the cache for this corresponding 75 block address is nothing but whatever the block address is there, block address modulo the number of blocks supported by the cache. Number of blocks supported by the cache. So here the block cache size equals to 64 blocks. So therefore, cache can able to support only 64 blocks. So whatever the number of blocks offered by the address space, so all of them has to be mapped to one of these 64 blocks. So for that, actually here we are using this particular mapping mechanism, block address modulo 64, that gives you the corresponding block number in the cache entry, in the cache. Right. So the 11th is the 11th location. 11th means if you start from 0, it will be the 12th location. Right. So address 11 in the cache corresponds to this particular block address center. Right. Is it clear?
Yes, sir.
Yeah, good. Yeah, then the next one is actually here, as we are so far we discussed about cache mechanism for our mapping policy of a cache to the main memory, right? Because the main memory obviously contains more of size, much bigger compared to the cache and all. But we need to map the main memory content into the cache, or we need to manage that most of the times whatever the CPU requires that has to be present in a cache and all. So that way you need to have some kind of a mapping mechanism where the more entries has to be placed into a limited number of entries offered by cache and all. So in the process, sometimes when a CPU asks for a particular address, particular instruction or particular data, so that may not be present in the cache and all. So that is known to be a miss, cache miss. We have seen this terminology. If it is present, known to be cache hit and all, right? And so there are different types of cache misses can occur, different reasons for this cache misses and all. One of them will be, as I already mentioned, that compulsory misses. Compulsory misses. So compulsory misses means just at the beginning, like when you start the program, at that time you don't have any knowledge about from where the control will start or which of the instructions has to be executed at the beginning and all. So we are not aware of that. So therefore we cannot fill up the cache. So because of that, the initial few references you can able to experience a misses and all, continuous more number of misses and all. So this is a compulsory one because this is at the beginning. So the cache is empty. So therefore, obviously, you will encounter the misses at the start of the program and all. So, sometimes program migration. Program migration means sometimes a process will be shifted from one core to some other core because we have suppose octa core or quad core was there, for example, and maybe the process may be there in the core 1, for example, and because of some scheduling where this process has to be shifted to some core 3, for example. So when your process is shifted from core 1 to core 3 at that time, so whatever the related contents, those also has to be shifted. But when you're shifted at the beginning, so therefore that cache at the corresponds to core 3, like that is not relevant to this one. So therefore we'll make it empty and then afterwards we'll start. So at the process migration means that is the one. And at the beginning, usually you have experience, a sequence of misses will be there. But those are negligible if you consider larger program under. Suppose your program length equals in terms of thousands or millions of lines and all. So at that time, when you execute all these instructions, at that time, the initial misses and all, those are very negligible and all. Because the moment once you have a miss, for example, you are bringing a block. A block here contains maybe 16 words or 32 words and so on. So with that, it tries to manage the spatial locality. And again, whenever you want the address which is not in this block, again you will find the miss. Again you will encounter the miss, and again you fetch that block, and again you have a spatial locality. So therefore, first initially, whenever you need a particular instruction or a data, which is not present in the block, then you will experience the miss and all. So these are known to be compulsory misses because there is no other way, nothing can be done in this case and all. Right. So the only way is that actually the one way to reduce these misses will be, like as I mentioned, increasing the block size. Instead of just having a block size equals to one word, then these compulsory misses will be more and more. So instead, if suppose if you increase the block size, then the compulsory misses can be reduced to some extent. But the problem is that if you increase the block size, very extreme cases and all to very higher orders, then it leads to some again other issues also. Like if you increase the block size, the penalty, miss penalty will be increased. Miss penalty means suppose if miss occurs, suppose if you increase the block size, for example, to for example 64 bytes, your block size equals to 64 bytes, right? And then first initially you will get a miss, and then we have 64 bytes, but the next reference happens to be not in this block, some other block, for example. And for that again, you will again a miss will be generated to bring that block into the cache here. Again, you need to have penalty because you need to bring the 64 bytes of data. If a block size equals to small, then the transfer time or fetching time will be less. If the block size equals to larger, then again it requires more time to fetch the entire block and all. That's what mean by the miss penalty and all. We'll see that what this miss penalty contributes to. One of these component will be transferring the data of that entire block to from main memory to the cache memory. So there are different components are there. So because of that, if a block size equals to larger, obviously intuitively also you can see that the miss penalty will be increased and all. Every time a new block has to be fetched means you need to have more time to fetch the block, and during that time the CPU will be idle, right? So that way it happens. And another thing is that suppose if you have a block size equals to very large, then the cache can accommodate only few blocks. Cache can able to accommodate only few blocks. With that, that also indirectly increase the miss rate and all. Because assuming that, as I mentioned, suppose we have like for example 64 kilobytes as a block size for 64 bytes is a block size for example, right? So in that it means that each block contains 16 words. Each block contains 16 words. Suppose for example your cache size equals to it can able to accommodate only 4 such blocks, for example, only 4 such blocks. So in that case, you can see that you have only 4 different possible blocks you can able to accommodate, right? And suppose the desired word, the desired instruction, if it is not present, then again you have to fetch the new block, right? And again, since the cache contains only these 4 blocks, and also therefore it also indirectly increases the misses also, miss rate also, because it can be block size, block higher the block size, it can able to accommodate the spatial locality. The spatial locality can be taken care. But we're not sure that the program generates the instructions only in sequences. Sometimes the control will move on to some other place, and again the instructions will be fetched from a new block and all. So therefore here, if the block size is very large compared to the cache size relatively, then in that case you have very few choices, very few blocks can able to accommodate. So that again indirectly increases the miss rate also. So that means to handle this compulsory misses, if you suggest to increase the block size, there are other issues also will be there, right? So therefore you need to have some trade-off has to be there. And there are other, this is going to be compulsory misses usually generate at the beginning, when you start of a program or a start of a new process, for example, at that time these misses will be resultant on. And this is the one of the solution. But again, when you go by this, you should be careful and all. What is the block size you have to take? It should be neither too large nor too small, right? And capacity misses means actually here the cache cannot accommodate all the blocks. That's true. As we have seen in the 32-bit address, you have 2 power 20 possible blocks are there. All those blocks cannot be accommodated by cache, right? So because of that, cache cannot accommodate all those blocks and all. When the program generates certain instruction, certain address, and that address is not available in the cache and all, then you have to go because it's not available because the cache has a limited size. So limited capacity. So because of that, the miss will come. So this is going to be capacity misses and all. Because of the limited capacity offered by cache and all, the miss, whatever the misses that are generated, those are known to be capacity misses and all. right? This is also obvious, but this will you can handle this cleverly by using the by exploiting the principle of locality, or by picking up the blocks which are most probably called by the CPU or most recently used by CPU and all. So those things, if you bring it to the cache and all, then you can able to minimize these misses and all. So this is not to be capacity misses. Capacity misses means this is due to the finite size or the limited size offered by a cache compared to the program size, because of the program size equals to, for example, 100 megabytes, for example, including data, everything and all. But your cache supports only 2 megabytes or 4 megabytes cache, for example. So in that case, you cannot accommodate 100 megabytes into the cache and all. So therefore, certainly at some point of a time, the misses will occur. So that is because of limited size of a cache. It's not to be capacity misses and all. The solution will be increase the cache size. But anyway, you cannot increase the cache beyond and all, because one problem is that the cache access time will increase. If the size is increased, that the number of entries will be increased, and to find out which entry corresponds to this and whether it corresponds to not. So for all these access time also will increase with the increase in the cache size. And not only that, the cache is very expensive and not affordable also beyond certain cache size and all. And not only that, and another thing is with respect to time constraints also, if the cache size is large, then the access time will be more. And you see that our limited, when CPU is accessing, CPU managed to perform its operation within a clock cycle. And a clock cycle is of order of a nanosecond or less than nanosecond. Suppose if the clock equals to 4 gigahertz, then the clock cycle equals to 0.25 nanosecond, right? So the CPU can able to manage its operations within that fraction of a nanosecond and all. And if the cache size is larger, and if some data has to bring it from cache, it cannot be done within the fraction of a nanosecond and all, if the cache size is very large. So that's where you cannot, even though you're affordable, you cannot increase the cache just like that, right? But because it will hamper the hit time. That means if the data is also, even though it's available in the cache, but you cannot bring it back or cannot use it within one clock cycle and all. So that's where the problem is if it are larger caches. Okay, then another one is going to be conflict misses and all. So it is also somewhat related to this one, because in the case of cache, as we have seen that multiple memory locations or the multiple blocks are targeted to single location. We have seen in case of direct mapped cache and all. As we have seen with simple example, we have 16 words are there in the main memory. There are only 4 word locations are there in the cache. Then it means that 4 of the words will compete for one location, right? So in that process, to fetch a particular, when the CPU generates a particular address and that is not there in the cache, in place of that there is some other block is there. You have to replace that block, right? And once you replace that, later on you may need that block again. So that kind of misses that are result, because after replacement, immediately if you require such blocks and all, and those misses can be viewed as a collision clashes and all, because of limited size. And one way is that you can increase the cache size, and other one is that actually increase associativity. We'll see that what is meant by associativity and all. So based on that, you can able to handle to some extent to manage the collision clashes to some extent. Increasing cache size is direct solution, but again there is a problem with that, right? And the increasing associativity, we'll see that what is meant by associativity and all, right? So these things will continue. Let's take a break for 5 minutes, and then we'll come back and then we'll start. So now what I will do is that I will stop the recording, and again I will start, because if the recording is too long, it's difficult for downloading and other things. I'm just stopping here. Okay, and again after 5 minutes